Okay, this week we're going to start talking about one of the specific variables we deal with in the meteorology world. Uh, and you all care about it. At least if you walked outside today, you kind of care about it. Uh, Temperatures are ridiculously cold right now. I noticed that several places in Ohio and West Virginia have temperatures anywhere from 0 to as much as 10 below zero this morning. So I would think you're kind of interested in what the temperature is going to do. And that's what we're going to talk about, how temperature is controlled and how it relates to the meteorology in the atmosphere. So, what are some of the causes that cause heat transfer? As temperature changes, we're transferring heat. And we're going to get into the definition of what is that, how does that work within the weather. A classic example of a place that's extremely hot is Death Valley. It holds the record, actually forever recorded on Earth, of 134 degrees in 1913. And we've approached that a few times here recently. Matter of fact, they've had times in the last few years that even have exceeded the 105 days where it reached 110 in a row uh, here recently. So, why is this such a hot place? One, it's actually below sea level. So, we remember temperature cools as it's going up. Well, it warms as it's coming down. So if you're down below sea level, it's even hotter than if you were at sea level. And it's a great place because it has no clouds almost. So have you very intense radiation. There are higher ridges around it. Air sinks down, warms in that process. So it has an ideal situation for getting really, really hot. So when you talk about temperature scales, temperature is really a measure of kinetic energy. Kinetic energy is molecules in motion. Kinetic energy basically means motion energy, energy derived from moving things. So molecules move. You're made up of molecules, the air is made up of molecules, and they move. So the more they move, the higher the temperature. The less they move, the lower the temperature. And theoretically, because we've never reached it, there is a point at which all motion ceases. That's supposedly absolute zero, or minus 459.67 Fahrenheit. So, if that is the case, at that point, we believe, according to all the theories and things, there'll be no electromagnetic radiation, and all molecular motion will cease. So, we're saying that since temperatures can't get any colder than that, since you can't have reverse motion, and temperatures reach absolute zero, kinetic energy goes to zero. So that is the coldest theoretical temperature we can have. How does temperature change? Take some heat, and heat can be measured in different ways. Calories, which are different than food calories, and a calorie basically is raising the amount of heat required to raise 1 degree of water, 1 gram of water, excuse me, by 1 degree Celsius. Joules, that's another energy term, and it is about 4.1868 joules per 1 calorie. And then there's BTUs, or British thermal units. Uh, I have seen hot water heaters that measure the amount of BTUs they use or whatever. So that is another measure of a way to measure the heat required, energy required to move the temperature 1 degree. So how do we measure temperature? Well, in the old days, we used to use mercury thermometers. Mercury would contract with the colder air and expand with warmer air. Now we use alcohol-based thermometers more, you see around. Uh, and we also have more sophisticated ones like this, where temperature sensors are inside it. Basically, it's an electronics. They measure the resistance change in electronic parts. By measuring that, they can be extremely accurate and very, very quick to respond to temperature changes. So, for example, uh, if you were driving along and you had this kind of thermometer, you would see minute changes in temperature as you're driving along the road. Because even over short distances, temperatures vary a lot sometimes. All right. There is a temperature gradient on Earth automatically. Why? We learned last week that more solar energy reaches the equator than it does the North Pole or South Pole. That means equator is hotter than those two places. So in order to get rid of that change or whatever, we're saying there must be a temperature gradient between the poles and the equator. And per the second law of thermodynamics, heat always is going to flow from higher to lower temperatures. The Earth, I'll tell you right now, it doesn't like differences within it. The atmosphere hates a difference. So if there's higher temperature somewhere else and lower temperature somewhere, the atmosphere is always going to be trying to correct that. And by the fact the way the radiation comes in, the way the Earth rotates, there will always be differences. But the atmosphere is always going to work to get rid of those differences. And how does it work to do that? It actually has radiation, as we talked about a lot last week, conduction, convection, and latent heat. Radiation is just what we talk about, energy and transferred through the air, through space, even through a vacuum. We learned a lot about that last week. The Earth absorbs radiation from the sun and releases some radiation, cooling itself. The atmosphere does the same thing. What's conduction? Well, have you ever heated something on the stove? Fried an egg? That's conduction. Temperature is moving, energy is being generated by that stove or whatever and being transferred through whatever frying pan, pot you're using to try to warm the molecules inside. That is a conduction. It takes place in the atmosphere. If you put your hand on a very hot surface outside, it's taking place there. Maybe you're putting your hand on ice outside, you're getting cold. All of that is conduction. Not the most productive way of transferring heat in the atmosphere, but it does occur. It occurs from the ground to the air and the air to the ground. Convection in a fluid, and gas is a fluid. Convection develops. In other words, warm air or liquid rises up in the convective process, cools as it's rising, eventually reaching temperature where it will fall back and repeat the process. It's a great big circle of air. Happens, you can really see it when you see little tiny cumulus clouds develop in the summertime or even in the wintertime. And they're just there. What that is basically a convective current in a local location. You see it when water boils. And sensible heating is conduction and convection, both combined. So a lot of the heating in the atmosphere does get from conduction and convection. The next one is latent heat. There's a substance in the atmosphere called water. And water changes state. It's the only thing that does in the atmosphere. In other words, it goes from a gas to a liquid to a solid or back and vice versa. When it's doing that, it releases a certain amount of heat or takes in heat. That heat is called latent heat. So if you have a solid and you're going to a liquid, you're melting. In order to do that, heat is required. And when you go from a liquid to a gas, more heat is required. In other words, if you look at the water boiling, you'll notice steam rising in the air. It required heat to make that happen. You want to go the other way. If you have water vapor that's condensing into a liquid like happens in clouds, then you're releasing latent heat in the atmosphere. And if you're freezing it, more latent heat is released. So actually that is a way of putting energy into the atmosphere, changing the temperature of the atmosphere, that's actually pretty efficient. When you have a cloud, the temperature is going to warm in that cloud because of the latent heat release. And water is one of the most difficult substances to change its temperature. We call things specific heat the amount of heat that will raise 1 gram of one substance 1 degree. And water is really, really tough to heat up. That's why the oceans take forever to heat up when they get a lot of sunshine on them. And so there's a resistance to change, and that's called thermal inertia. Large bodies of water have that. That is why they don't cool very quickly in the winter as it gets into winter, and they don't rise their temperature real fast when they get into summer. So they control a lot of temperatures near the coastline. So if you live near an ocean, they have a major influence on the temperatures. And here you can see that in comparison of maritime climate like San Francisco. You'll notice temperature doesn't get real cold in the winter, nor does it get real warm in the summer. However, go inland like St. Louis, significantly colder in the winter, much warmer in the summer. It doesn't have that maritime influence. All right. This is interesting in the sense that the Earth receives radiation from the sun. There is a net gain of energy by the Earth's surface. However, the atmosphere actually sends more radiation out, that infrared radiation, than it absorbs of the ultraviolet. So the atmosphere is actually a net cooling. The Earth's temperature stays pretty much the same. We've minor changes. So in order for that to happen, the Earth's surface needs to transfer heat to the atmosphere to make up that difference, keeping it not changing a whole lot. And here you can see all the fun complexities of how heat is exchanged between surfaces in the atmosphere. And if you wanted to make a weather forecast using a numerical model, every one of those has to be figured out. Otherwise, you couldn't forecast the temperature changes. So as latent heat is released into the atmosphere during cloud development, what we're finding is that latent heat then helps to warm the atmosphere. It is actually the most important cooling process on the Earth. Almost 75% of the Earth is water. So the fact that water condenses in clouds in the atmosphere is a way of releasing heat from the Earth to the atmosphere, keeping the atmosphere warmer. Another looking at convection. Think about a cumulonimbus cloud, a big cumulus cloud. What it does, it gets heat from below. Conduction heats the bottom of the atmosphere. Convection takes place, lifts that air up. Then, as it gets cool, that air as it's rising, it condenses the moisture in it, and latent heat is released. This is a great way to take heat from the Earth all the way up to the top of the atmosphere. So we talk about sensible heating, and then there's latent heating. Well, the drier you are, the more sensible heating. And if you get a lot of rain, the more latent heating. So places like Yuma, Arizona, where it never rains a whole lot, get a lot of sensible heat. More tropical or even more areas that get more rain can change, and they can change by season. During the summertime, for example, in Madison, Wisconsin, you'll see there's more latent heat released than there is sensible heating. All right, now we know that the atmosphere is colder because they get less radiation up around the poles. And the atmosphere doesn't like that being that way. So it's going to work to change that. How does it do that? One of the ways is air mass exchanges. Cold fronts, warm fronts, they move air around. There's a front where there's strong contrast in air. and that is a way of exchanging heat between the tropics and the poles. Another one is storm systems. Extratropical lows, even tropical storms, especially tropical storms as they move north, bring large volumes of moisture and heat with them. Ocean currents. The Gulf Stream, for example, pulls a lot of heat from the tropics to the north, moderates the temperatures along the east coast, has a major impact on Iceland and England. So air masses are just, as we've talked about already, large areas of the same temperatures, humidity, because they form over an area. Air masses can form, for example, over the Gulf of Mexico, you would have a maritime tropical. If you had an air mass form up over northern Canada or Alaska, that would be a very dry air mass. There's not a lot of water up there. It would be a very cold air mass, especially in the wintertime, like we're getting right now. So that would be a continental polar air mass. And here you can see the heat sources and all from the water. The ocean's having an impact. So why is there weather? Weather is caused by all these temperature gradients. If we didn't have a temperature gradient, we wouldn't have weather. So because of that, this radiation converts that energy to kinetic energy, and it causes the winds, air mass motions, seasonal temperature changes, everything. And because radiation changes from the time of day to the time of year and where it's at, that has an impact. And it takes a while for the atmosphere to adjust. For example, it estimates that the lag time in the U.S. is about 27 days, and if you're along the coast, about 36 days from when the sun is actually coming back towards you. Now, here you can see the radiation coming in. There's definitely more radiation in the summer. Notice how much further north you get in our summer. Very low radiation in the wintertime. But wow, almost as much radiation is coming in as Kansas City, Missouri, and beats Kansas City probably March or April. During the day, because we have temperature changes, we talked about the very first chapter, ask you a question. The question was, why does it get hot us in the afternoon, about 2 or 3 o'clock? Well, here's the reasoning. During the night, we're losing cooling. So we have a deficit. The air is cooling because infrared radiation is going out to space. There is no ultraviolet radiation coming in. Conduction from the Earth's surface is gradually being cooled as well. All of that cools down the temperature. During the day, especially during the morning, intense ultraviolet radiation reaching its max about noon. But that ultraviolet radiation from the sun doesn't end. It keeps going. However, the infrared radiation from the Earth is slowly increasing because it's getting hotter, so that they balance each other out about 3 o'clock in the afternoon usually. Summertime's a little later, wintertime's a little earlier. So that's when the highest temperature of the day is reached. If you have bare soils and no water, because no evaporation is occurring, temperatures are going to warm faster. That's why during a drought, some of the hottest days are going to occur. However, if you have a lot of precipitation, you're going to have a lot of water on the ground, a very moist ground. Some of that energy is going to be used to evaporate that water. And if it's used for that purpose, it can't be used to heat the air temperatures. You wind up with the air being cooler. After a rainstorm for a couple of days, the air tends to be a little cooler because of that. However, if it's a drought, just the opposite. Snow has a major impact on temperature. Why? Snow has a huge, probably the highest albedo on Earth. What does that mean? It means it reflects all that sunlight that comes in from space. So it doesn't get to heat up the surface. It doesn't get to heat up the atmosphere. So when you have a fresh snowpack, and you can see it by the fact that how bright it is outside. That is going to keep the temperature significantly colder. Many times in winter, you can watch as the snowpack moves along. Along that snowpack edge, there is a significant temperature gradient. Why does that develop? Because the snow keeps everything cool. The area on the other side is warming faster. Many times, fronts literally develop right along that area. And how do we move all this cold air from one part of the world to another? Well, we have what we call cold advection and warm advection. We'll go into that in a second here. And finally, there's the urban heat island. Urban heat islands trap heat. If you live downtown in a big metropolitan area, the sun is going to hit those buildings, and it's going to keep warming the buildings, and they're going to put that heat back into the city so that it winds up being 7, maybe even much as 10 degrees warmer in the bigger cities. Something that pays a major impact if you live downtown in summer, and if you're getting into a heat wave. That's why the downtown areas are the most dangerous in summer. So with that, one last thing I wanted to show you. Here is a temperature gradient. The solid lines are temperature. I want you to look just along the East Coast. This is today. Notice the pack, how tight these solid lines are. And notice the wind blowing into it here and towards it the other direction, increasing that gradient. That is cold advection. It's also frontogenesis. There's a front developing there. But there's cold advection coming from the inland areas and warm advection from the Gulf Stream coming the other way. That's why a lot of storms develop right along the east coast of the United States. You have the Gulf Stream keeping the air warm. You have the cold air coming down from Canada. They meet, you produce a tremendous temperature gradient. Same thing's happening down in the Gulf of Mexico, and you can see it. Look at all the cold air advection into the state of Florida right now. Strong northwest winds perpendicular to the isotherms, which are lines of equal temperature, pulling the air down. The stronger the wind, the tighter the temperature gradient, the stronger the advection. And it can be cold or warm advection. All you've got to do is look where the air comes from. If the air is colder where it's coming from, that's cold advection. If it's warmer, warm advection. I hope you got a little bit out of this. Now you understand a little bit how temperature forms. Let me know if you have any questions.